The drag force is a very important concept in classical mechanics, as it plays a role in many applications that involve projectiles moving through fluids. Surface area is also an important factor governing the behavior of both projectiles and falling bodies. One of the fundamental objectives of classical mechanics is to arrive at mathematical equations that can accurately describe the motion of an object or system. Most motion in real-world applications involve resistance forces and drag. In this experiment, the drag force was investigated by dropping 5 objects of varying surface area and constant mass and volume through a given height of water. There were 5 configurations under investigation, which all have the same mass and volume so that the gravitational and buoyant forces are the same across all trials. 4 of these configurations are boxes with varying surface area, while the 5th configuration is a compact thin rod, which will serve as the control, due to the negligible drag force. Each configuration is made out of the same amount of aluminum foil. Additionally, each configuration had a nickel coin fixed at the center of mass to better enable it to sink. Each configuration was released from a given height from the bottom of a swimming pool, and the time it took for each configuration to hit the bottom was recorded. 5 times were recorded for each object, and the average of these times was taken. These data points were then plotted so that the relationship between cross-sectional area and time of flight can be determined. This data is presented on the following graph. In addition, theoretical models for the flight time of each object were calculated by use of Newton's second law. The forces acting on an object moving through a dense fluid like water are as follows: the gravitational force, the buoyant force, and the drag force, whose general form is used in our model. Solving the differential equation associated with Newton's second law, theoretical times of flight were obtained for each configuration. This data was then used to produce the following graph relating the cross-sectional area to the time of flight. Superimposing the theoretical and experimental graphs, it can be seen that both models agree quite well. As a result, it was found that the time of flight for any given projectile behaves similarly to the square root of its surface area. As surface area increases, the time of flight consequently increases. However, the rate at which it increases decreases as the surface area gets larger and larger. This conclusion is supported by both experiment and theory, and the generalized drag force was also verified by the experimental trials.